Hey everyone, it's Dr. Walker. This is the second part of video 53C on center of mass. I want to talk about two more topics. The first one being finding the center of mass of an extended object. An extended object is a system containing of a large number of small mass elements. We usually think of an extended object as just an object that has some definite size and shape. That is versus just a point particle, right? That is just a point and has no shape and no size. All right, how do we find the center of mass of our extended objects? Let's kind of, this is the expression here, but let's just derive it real quick just to understand what's going on. What we're going to do is we're going to divide our object into a whole bunch of very, very, very small little masses. We're going to say that each little mass has a mass delta mi. So now, how would we find the center of mass of this? Well, we can write down our expression for the center of mass. Let's just look at the x-coordinate just to make it a little bit easier. And leave some space here because we're going to write something in just a second. But the definition is 1 over m times the sum of the product of all the positions times their masses, and the masses being delta m. So what we're going to do now, in order to represent this extended object, we want these masses to become really, 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 really small so we can more exactly approximate our object. The smaller the mass, the more we can have defined the exact shape and size of this object. So we're going to take the limit as the delta m's approach 0 of this whole expression. And as you can imagine, what's going to happen is that the summation is going to become an integral, the integral of x dm. So if you're just looking for the x-coordinate of the center of mass, this is how you would do it. Now, we're definitely going to do some examples because how in the world do you know what dm is, right? How do we do this? We're going to learn best by example. But we can generalize this to the position vector of the center of mass of our extended object being our center of mass is equal to 1 over m times the integral of r dm. So definitely look for the examples. I like to really elaborate on this topic and do a lot of examples because you have to be able to have this skill of doing this kind of integral in physics 2 as well. So it's good to start now. Before we end this video, I want to talk about one last thing, and that is the velocity of the center of mass. If we want to find the velocity of the center of mass, all we have to do is take the derivative of the position vector for the center of mass. Take the derivative with respect to time. So we can replace this r center of mass position vector with its definition. So we're going to take the derivative with respect to time of 1 over m times the sum of all of the masses times their position vectors. And now we can see that the position vector is the only thing that is going to depend on time as you're moving. So we can take all of the masses outside of the derivative. So we're going to get 1 over m, sum of mi, and then we're just going to have dri dt. So we're going to sum up all of these. And we can see that if we have the derivative of the ith position vector with respect to t, that is just vi. So we can rewrite this as 1 over m, sum of mi, vi. So this is how we get the velocity of the center of mass. We just sum all of the masses times their velocities, divide by the total mass. In order to really emphasize the importance of this, let's reorganize this equation that we just found. So we just found this equation, V center of mass is equal to all of this. Let's multiply both sides by capital M, and then we'll just have the summation on the right-hand side. So I've just reorganized the equation that we just found. Let's really analyze what it means. It means that this mv center of mass is equal to the sum of all of the momenta, right? So that means that it's equal to the total momentum of the system. So what's really significant about this is that the total momentum of a system, that's what I wrote here, the total momentum of a system is the same as that of a single particle, right? This is just one single particle of mass m that is moving with the velocity center of mass. It's moving with the center of mass velocity. So this also helps us understand that when a system is moving, right, a system of a whole bunch of objects, we can just imagine that we just have one single particle that is moving with that center of mass velocity. Let's do one quick question. This is a problem called the exploding projectile. We see that a projectile explodes and goes off into all directions. And we want to know about the motion of the center of mass of the system that is made up of all of these fragments that are going in all the directions. So before the projectile explodes, we know that it's undergoing projectile motion. It's only under the influence of gravity. Now, what happens after it explodes? Well, during the explosion, there's no external forces, right? Explosions have all internal forces. When there's no external forces, we know the momentum is conserved. So the total momentum that we just saw on the previous slide, right, that's constant. So we saw that the total momentum is just mv center of mass. So if this momentum is not changing, then the velocity of the center of mass is not going to change. And that means that the center of mass of the projectile is going to keep moving along the parabolic path. One thing that this tells us, let's say that this projectile exploded into two equal pieces. Let's say that one of the pieces of the projectile went all the way over here. Well, now you would know where the other piece would land. Because if you know that the center of mass continues its motion and the center of mass lands here, right, then that means that if one half of the projectile is here, then the other half of the projectile is going to be on the other side of the center of mass at the same distance, because we know that the center of mass is the average position of all of the masses. So that was it for this video. Take a look at the guided examples where we get to practice finding the center of mass of several different objects.